Hello friends, today we are going to see how we can understand feedback amplifier and its type in just 10 minutes. Let me tell you, we are going to see all basics concepts as well as advanced concepts that will be helpful to solve gate problems. Okay, so let's start with the video. So first thing what we should know is what is feedback. Feedback is a process of injecting some part of output to the input. Okay, so you can see in this connection, this is a feedback connection diagram. Here you can see this is a feedback factor, and from this terminal we are taking some part of output voltage and we are giving to the input through this feedback factor. Okay, here the process which we use to get the output voltage is sampling, and the process where we add the output voltage to the input is mixing. Okay, so basically here we are doing mixing and here we are doing sampling. Okay, we will see all types of mixing as well as all types of sampling also. Okay, now we know what is the feedback connection, what is feedback. Okay, now let us see what are the types of feedback. There are two types of feedback, positive feedback as well as negative feedback. For positive feedback we say it is a regenerative feedback, and for negative feedback we say it is a degenerative feedback, because in positive feedback the gain increases and in negative feedback the gain decreases. We will see how it is getting done. Okay, now let us derive the closed loop gain from this connection. This is a open loop gain which is equals to VO by VI. Okay, this is what your open loop gain equation, and this VF can be written as beta into VO. This is what I have written here. Okay, and this VS is basically VI plus VF. Okay, so this is what I have written here. Now since we know Vf is equals to beta Vo, so we can replace in this equation. So Vs will be Vs equals to beta Vo plus Vi. Okay, so now we have this equation, and we know for the closed loop gain the formula is output upon input. Okay, so this output upon this input. For open loop gain it will be this output upon this input. Okay, so we have Vo by Vs as a formula of closed loop gain, and since both the output parameter and input parameter are in terms of voltage, so this gain can be said as voltage gain. Okay, so we can also say this is voltage gain, which will be equals to Vo upon Vs. We know Vs is this, so if we put here we will get Vo upon beta Vo plus Vi. And now if we take Vi common here, so we will get Vo by Vi 1 plus beta Vo by Vi, since this term doesn't have Vi, so we will divide by Vi here. Okay, so we will get A upon 1 plus A beta. Okay, this A is a open loop gain. This is what I have told you here. Vo by Vi will be A 1 plus beta Vo by Vi. This Vo by Vi again is A, so we can write it as A upon 1 plus A beta. So you can see this is our AF, basically closed loop gain. There are two important factors that we should know, is that is sensitivity and desensitivity. Formula of sensitivity factor is 1 upon 1 plus A beta, and for desensitivity factor is 1 plus A beta, simply this numerator. Okay, now we will see the types of mixing as well as the types of sampling. Okay, now let us see the types of mixing. We know what mixing does. Okay, we usually use mixing to mix the input as well as a feedback parameter. Okay, now let's see first type we are having voltage mixing, and it is also called as series mixing, because for voltage mixing we usually gives the output of this feedback factor in series with this input connection. Okay, so you can see we are giving output of this feedback factor in series with this input connection. Okay, so this is what our voltage mixing is. And also you can see this is our input resistance, right? Input resistance of open loop gain, and this will be a complete input resistance basically for closed loop connection. So here you can see, since we are adding something in series, so the input resistance is going to increase, right? In series the resistance increases, in series the resistance adds up, and in shunt the resistance decrease, right? Since we know 1 plus 2 will be 3, while 1 parallel to basically 1 into 2 upon 1 plus 2 is going to be 2 by 3. So you can see it is getting decrease, and here it is getting increase. So whenever we are giving something in series, then our resistance will increase, and whenever we are giving something in shunt, then resistance is going to decrease. So here we can see in current mixing, it is also called as shunt mixing, because the output of this feedback factor we are giving in shunt. Okay, so you can see here this is our input resistance and this is our complete input resistance. So you can see here the input resistance is going to decrease, right? Because we are adding a shunt here. Okay, so here you can see the resistance is going to decrease. Now let's see the sampling. Sampling decides the output resistance, and we know why sampling is required. Okay, sampling is required to take the samples from the output. Okay, first we have voltage sampling. This is also called as shunt sampling. because to take samples in terms of voltage we are going to add a shunt here. Okay, so you can see the complete output resistance is going to decrease. Okay, while in current sampling, which is also called as series sampling, because the current sample is taken by the output connection in a series way. Okay, so you can see here we are taking the current sample in series. Okay, so that's why you can see the output resistance is going to increase. Okay, this will be very much helpful to solve the problems on this feedback topologies. Okay, one thing you should note is that here in voltage mixing we are mixing in series, while in voltage sampling we are taking samples in terms of shunt. Okay, so you can see both are opposite to each other. Whatever thing is in mixing, it will be opposite in sampling. Okay, here it will be series, here it will be shunt, here it will be shunt, here it will be series. Okay, so take note of it. Okay, now let's see classification of feedback topology. We have four topology. First one is voltage series topology, voltage shunt, current series, current shunt. Okay, before going to the connection we should know the format this term is written. Okay, so you can see here we have a voltage series, right? Voltage series. Okay, so this first term says about the output and this second term says about the input. Okay, so whenever you get this type of format like voltage series, current shunt, then this first term says that in output we are having a voltage sampling and at input we are having a series mixing. Okay, so first one, let's see, we have a voltage series. Okay, basically we have a voltage sampling and a series mixing. Okay, so you can see we are having a voltage sampling here and we have a series mixing here. Okay, this is our open loop gain, this is our feedback factor, and you can see this output voltage is getting mixed in series. Okay, and here the output voltage is taken. Okay, so you can see for voltage sampling we have a shunt here and for voltage mixing we have a series here. Okay, now let's see what will be the effect on input and output resistance. Okay, so this is our input and output resistance for open loop gain, basically for this block, and for the complete blocks we have RIF or ROF, which is also called as input resistance with feedback. Okay, and it is also called as output resistance with feedback. Okay, so since you can see here we have mixed in series, so this input resistance is going to increase. Okay, so that's what you can see, we have multiplied desensitivity factor with RIF, so the resistance is going to increase. Okay, and here you can see since we have used the voltage sampling, that's what we have done by connecting it to shunt. Okay, so you can see the output resistance is going to decrease. So you can see the output resistance with feedback is written as RO by D. Okay, so this is going to decrease the output resistance. Okay, so you should take note of it because this will be helpful to solve problem. Well, in next video I will show you the trick to solve this also, but it's better to know the concept. Now let's see the another name of this. Another name of this voltage series is series shunt, voltage and voltage amplifier. Okay, so these are different format, this is different format. Okay, in this format here we have a input and here we have a output, while in this format here we are having output and here we were having input. Okay, except this one, all other uses this format only, that is first one will be input and another one will be output. Okay, so this is what you can see in series shunt. What is means is in input we are having a series mixing and at output we are having a shunt sampling. Okay, so this is what series shunt means. Okay, and the second one is saying we are having a voltage mixing and voltage sampling. Okay, and third one is saying voltage amplifier. Why? Because here the AV is VO by VI, or you can also understand in this way, like we have a voltage sampling at output and voltage mixing at input. Okay, basically at output also we are having voltage and at input also we are having voltage. Okay, so you can see this is what our voltage amplifier gain is, right? So that's why it is also called as voltage amplifier. Okay, now let us see voltage shunt topology. This is the second one. This will say we have a voltage sampling at output and this will say we have a shunt mixing at input. Okay, so you can see we have a shunt mixing here and we have voltage sampling here. Okay, and the open loop gain here can be represented by AR or basically RM. So let's see the effect of the resistance here. So here you can see we have a shunt, so input resistance is going to decrease here. Here we have shunt, so output resistance is also going to decrease. Okay, so ROF will be RO by D. Okay, wherever you are going to decrease, you are going to divide by desensitivity factor. Wherever the resistance is increased, you are going to multiply it by desensitivity factor. Okay, so now let's see the another name of this topology. So this can be also said as shunt, right? So this is what it is saying. Shunt mixing is also called as current mixing. So that's what second name is, current voltage. Okay, current is mixing, voltage sampling, current mixing, voltage sampling. Okay, and this is also called as trans resistance amplifier because we are having a output voltage and input current. Okay, this is what our RM says. Okay, so you can see we are saying this as trans resistance because this is the resistance which is in terms of output voltage and input current. If it was output voltage and output current, so we will directly say it as output resistance, but here we have output voltage and input current. That's why it is saying that output voltage is getting transferred to the input. Okay, so that's why it is saying trans resistance. Okay, and this is what this equation says. Okay, now let's see third one we have current series topology. Current, it means we will have a series sampling and series mixing, right? Series mixing and current sampling. Okay, so this is what this format says. Okay, and let's see the effect on resistance. Effect will be like, here we have a series, so resistance is going to increase, so RIF will be RID, and here it will be ROF will be equals to ROD. Why? Because we have a series here. Okay, and the open loop gain can be written as AG and GM, basically trans conductance. Okay, so this is the notation of trans conductance here. Okay, another name of this topology will be series. Why? Because we have a series mixing here and series sampling here. Okay, also it can be said as voltage current. Why? Because we can say series mixing as voltage mixing and output as current sampling. Okay, so this is what your input voltage mixing and output current sampling. Okay, also it can be said as transconductance amplifier because we are having output current and input voltage. Okay, so this is what the gain of this amplifier. You can also refer it as we have a current sampling, basically output current. Okay, and at input we are having series mixing, basically voltage mixing. So at input we have a series voltage mixing. Okay, so by this also you can refer it. So you can see this will be trans conductance amplifier gain. So that's why this topology is also called as trans conductance amplifier. Okay, last one we have a current shunt topology. Current in the sense it means at output we will have a current sampling, and shunt it means at the input we will have a shunt mixing. Okay, so this is what you can see, shunt mixing and current sampling. Okay, this can also be written as series sampling. Okay, one in the same, only the name is different. Now let's see the effect on resistance. So you can see here we have a shunt connection, so input resistance is going to decrease. Here we have a series connection, so output resistance is going to increase. So that's what ROF equals to ROD, RIF is equals to RI by D. Okay, and the open loop gain can be written as AI. Okay, now let's see the another name of this topology. This topology can be said as shunt series, right? So this is what this name is saying, shunt series. Another name is current. Why? Because this shunt can be said as current mixing, right? And our output we have a current sampling, so current mixing, current sampling. So this is what this name is signifying. Okay, current topology. And it is also called as current amplifier. Why? Because the gain of this amplifier will be AI is equals to IO upon II, output current upon input current. Okay, you can also verify it by the sampling and mixing. So you can see we have a current sampling, so this is what IO is saying, and here we have a current mixing, this is what your II is saying. Okay, output current upon input currents. Okay, so that's why it is also called as current amplifier. Okay, hope so you understand all this concept. We are going to use this concept to solve the numericals based on this topic. And hello friends, today we are going to see the trick to identify the type of a feedback amplifier. Okay, let me tell you, after this video you are going to identify any type of feedback amplifier in just a second. Okay, so let's start with the sum, and there only we will see the trick. So first sum we are having from EC 2003, and we have to identify the type of a filter. Okay, and the circuit is given here and the option is here. Okay, so first take a look how I solve this sum, and then I will show you the trick. So the answer is voltage shunt directly. Okay, so you can see the answer will be this voltage shunt. So let's see the trick by which I solve this sum. Okay, so the thing which you should know is, let's say we have one element here. Okay, and if the feedback terminal and the output terminal is same, basically this output terminal and the feedback terminal is same, this is our beta feedback factor. If this feedback terminal and the output terminal are same, then you will say the sampling is voltage sampling. If it is different, basically if it is like this, like So you can see we have output terminal as this two terminal and feedback terminal as this two terminal. So you can see both are different. So whenever you come across this condition, it means the sampling is a current sampling. Okay. And similarly, if you get this thing, if both the input terminal as well as feedback terminal is same, then you will say the mixing is current mixing. Okay. Or you can also say as shunt mixing. Okay. And if these two terminals are different, then you will say it is a voltage mixing or a series mixing. Okay. Basically I'm telling like this. Okay. If these two terminals are different, then you are going to say this is a voltage mixing or a series mixing. Okay, so you can see the difference between both the sampling and mixing. Okay, here the voltage sampling we have shunt, and here for voltage mixing we have a series here. Okay, in my previous video where I have taught you how you can understand feedback amplifier in just 10 minutes, in that video I have explained this thing in a detailed fashion. Okay, so it's better that you watch that video first and then continue this video. Okay, so from this discussion what we can conclude is, if output and feedback is same, then we will say it is voltage sampling. Okay, and if it is different, then we will say it is a current sampling. Okay, and if input and feedback are same, then we will say it is a shunt mixing or basically current mixing. Okay, and if it is different, then we will say it is a voltage mixing or a series mixing. Okay, so from only this thing we can identify any type of feedback amplifier. Okay, so let's see this thing in the sum. Okay, so you can see here we have a output terminal. Okay, from here we take output, right? So this is your output terminal and this is your feedback element. You can see feedback terminal as well as output terminal are same. Okay, so we will say here voltage sampling is done, right? And here you can see this is our input terminal and this is our feedback terminal. Okay, so you can say both are at the same terminal, so you can say it as shunt mixing. So from this we can say the type of feedback amplifier is voltage shunt, right? So you can see this D option will be correct. Okay, the another name for voltage shunt is, I know you know it, right? Voltage shunt. This is output, this is input, and for another name we usually take input first and then output. Okay, so we can also say as shunt or current voltage, or we can also say it as V by I. So it is basically a trans resistance amplifier. Okay, all this thing I've discussed in my previous video. If you don't know, you can watch my previous video. Now let's say this sum here also we have to identify the type of a feedback amplifier. You can see here the output terminal as well as the feedback terminal is different. So from this what we can say, it will be current sampling, right? Current sampling or a series sampling, one in the same, right? And here you can see this input terminal and this feedback terminal are same, so we will say it as shunt mixing, right? So the answer will be current shunt. Okay, now let's say this sum, this is of EC14 and we have to identify the type of feedback amplifier. Okay, now here in this circuit you can see we don't have a direct feedback element. Okay, in all this sum you have seen we were having a feedback element. From this we were guessing our type of feedback amplifier, but in this circuit we don't have a direct element. Okay, so in this type of circuit only we have to think more. Okay, so you can see here we don't have a direct element, so what we are going to do, we are going to use the ground here. Okay, so you can see we have a ground here. You can see the current from this RE flow through this ground to the input, right? So we are going to use this. Okay, so you can see here we have a output terminal and we are considering this as our feedback element. Okay, because from this ground we are getting some part of the output. Okay, so we will say this is our feedback element and this is our output terminal. Okay, so you can see both are different. You can say the sampling as current sampling, right? So we have a current here, and for input you can see the current from the feedback terminal is reaching to the input in a series way. Okay, so that's why you will say it is a series mixing. Okay, so only for this condition you have to change the way of your thinking. Okay, so the answer will be current series. Okay, so the answer will be this B option. Okay, now let's see the special case of this circuit. Let's say we have a circuit like this, RC, this is our transistor, this is our RE, and this is our input voltage. Okay, now instead of this collector terminal, the output is taken from the emitter itself. Okay, and we have to identify the type of a filter. Okay, so for this also we are going to use the same way. As you can see here, we don't have a direct element. So we will use the same concept of this ground and we will consider this RE as a feedback element. So here you can see the output and the feedback is taken from the same terminal. Okay, so that's what you will say the sampling is a voltage sampling. Okay, and for the mixing you will say as this current from feedback element is flowing through ground to the input terminal in series fashion, so you will say the mixing is of series mixing. Okay, so the answer will be voltage series. Okay, for this it was a current series, and for this the type of feedback amplifier is voltage series. Okay, so take note of it. Now let's say this is of IS objective paper. Okay, and we have to identify the same thing, that is type of a feedback amplifier. Okay, so you can see from this terminal we are taking output, right, and this terminal is a feedback terminal. Okay, so you can see both are different, so it will be current sampling. Okay, and for the mixing you can see both the feedback terminal and the input terminal are connected to the same terminal, so we will say here the mixing is a shunt mixing. Okay, so the answer will be current shunt. Okay, now let's say this question, this is also a IS objective question. Okay, and we have to find the same thing. So you can see here we have a direct feedback element, so we will use the same trick. Okay, this is our output terminal, this is our feedback terminal, both are different, so we will say the sampling as current sampling, and for mixing you can see the feedback terminal and the input terminal are connected at the same terminal, so we will say the mixing is shunt mixing. Okay, so the answer will be current shunt. Okay, now let's see more sum. Now let's say this sum, this is of AC40 and we have to identify the same thing, that is the type of feedback amplifier. Okay, so here also you can see we have this as output terminal and this is also a feedback terminal. Okay, so both are connected at the same terminal, so we will say this is a voltage sampling, right? And for input you can say both the feedback as well as input terminal are at the same point, so we will say the mixing is a shunt mixing. Okay, so the answer will be voltage shunt. Okay, now most of people have a doubt, like we usually give the input from the base. Okay, so they consider base as an input terminal. Okay, but this is not true. The terminal from which you are giving input, that will be your input terminal. Okay, and the terminal from which you are taking output, that will be your output terminal. Okay, so don't consider any terminal as a fixed input or output terminal. Okay, it will depend upon your circuit, from what terminal you are giving input and from what terminal you are taking output. Okay, so now let's say the another sum. This is based on the op amp and we have to identify the same thing, basically the type of feedback amplifier. Okay, so here you can see this is our output terminal and from this terminal only the feedback is taken. Okay, so we will say that sampling is a voltage sampling, right? And you can see for mixing both are at the same terminal, so the mixing will be shunt mixing. Okay, so the answer will be voltage shunt, right? Sorry to say, but this is the wrong answer. Why? Because you can see the input is connected to this terminal. Okay, and that is what I have told you, the terminal from which you give input, that will be your input terminal. Okay, so don't consider any terminal as a fixed input or output. Okay, so this is what you can see here, we are not giving any input. Okay, so this is not our input terminal, this is our input terminal. Okay, so the correct answer will be voltage series. Why? Because this feedback terminal and input terminal are different. Okay, so the mixing will be series instead of shunt. Okay, so take a note of it, you always do this type of mistakes in exam. Okay, so be aware. Now let's say this sum, here also we have to find the same thing, that is the type of feedback amplifier. Okay, so you can see we have this output terminal and from this terminal only the feedback is taken, so we will say the sampling is voltage sampling. Okay, and for this you can see this is our input, so this will be our input terminal and this is our feedback terminal, both are at the same point, so we will say the mixing is shunt mixing, right? So the answer will be voltage shunt. Okay, and now let's say this sum, here you can see both are at the same terminal, so it will be voltage, both are at the same terminal, so it will be shunt mixing, so the answer will be voltage shunt. Okay, so you can see if you know the trick, you can solve this type of option in a second. Okay, so that's it for today. Hope so you like this video, so please hit a like button and please do share with your friends and subscribe to my channel. Thank you. Hello friends, today we are going to see the trick to identify input and output impedance of a feedback amplifier. Let me tell you, this will be the last trick on the chapter feedback amplifier. We have already seen how we can understand feedback amplifier in just 10 minutes. We have seen the trick to identify the type of feedback amplifier in just 1 second. And this one is the last one where we are going to see how we can identify input and output impedance of a feedback amplifier in just 1 second. Okay, so without wasting the time, let's see the contents which we are going to see. We are going to see the trick to identify increase or decrease in the input and output resistance in just 1 second. Then we are going to see the trick to get the exact value by which input and output resistance is getting increased or decreased. That will be in 10 seconds. Then we will also see the common mistakes by which we get negative marks. Yes, this one is very important. Okay, so let's jump directly to the sum, and there only we will see the trick. Okay, so first sum is from EC 2002 and EC 2004 as well. The question was almost same, just there was a change in wording. So let's see the question. In a negative feedback amplifier using voltage series, okay, that is voltage sampling, series mixing, feedback, and the options are input resistance decreases and output resistance decreases, input resistance decreases and output resistance increases, input resistance increases and output resistance decreases, input resistance increases and output resistance decreases. Okay, so we have to identify whether the input resistance is getting increased or decreased, or output resistance is getting increased or decreased. Okay, so the trick to solve this type of question is you have to attack the type of feedback amplifier you have. Okay, so the feedback amplifier which we have is voltage series here. Okay, so voltage series, and we know the format of this naming, right? This says that at output we have voltage sampling, right? And this says at input we have series mixing, right? I know you know this. If you don't know, then you can watch my previous 2 videos. Okay, now we have to identify the effect on input resistance and output resistance. To do that, we are going to identify the connection in input and output side. Okay, so you can see at output we have voltage sampling, and we know to do the voltage sampling we take a shunt connection, right? So what does it means? That you are connecting a shunt resistance across an output resistance of this block. Okay, so what you are going to get is that effective resistance is going to decrease, right? So if you connect two resistor in parallel, the effective resistance is going to decrease, and if you connect the resistance in series, the effective resistance is going to increase. So you can see here the effective resistance is going to decrease here, so you will say that output resistance is going to decrease, and for input you will attack on this. Since we know the mixing is here a series mixing, okay, series mixing, it means you are going to have the connection like this. Okay, this will be a feedback factor and you are going to have the connection like this. Okay, so you can see this block will obviously have some resistance, and you are adding some resistance in series, so you are adding some resistor in this kind of, so you can see the effective resistance is going to increase. Okay, so the answer of this question will be input resistance is going to increase as the connection is series, and output resistance is going to decrease as the connection is shunt. So you can see the correct option will be C. So basically we have to tackle this question in this way only. I was explaining, that's why it took me more time, but from now onwards we are going to solve this type of sum in just a second. Okay, now let's see second sum. Second sum is of EC 2007. The effect of current shunt feedback in an amplifier is to increase the input resistance, decrease the output resistance, increase the input resistance and output resistance, decrease the input resistance and output resistance, decrease the input resistance and increase the output resistance. We are going to use the same trick. First we are going to tackle the naming. The naming here is current shunt. All this is the game of mixing and sampling. If you are aware of the different type of connection in the mixing as well as sampling, you are going to solve this type of question in just 1 second. So you can see here we have current shunt, right? This will say about the output sampling and this will say about the input mixing, right? So at the output we have a current sampling. Current sampling basically a series sampling. So series sampling, so effective resistance is going to increase, right, because of this series. At input you have a shunt, it means you have a shunt mixing. Shunt mixing, it means the effective input resistance is going to decrease, right, because of this shunt. Whenever you get a series, the effective resistance is going to increase. Whenever you get a shunt, the effective resistance is going to decrease. Okay, so the answer will be input resistance is going to decrease and the output resistance is going to increase because of this shunt and series. Okay, so the correct option will be this D. So you can see if you know this type of trick, you can solve this type of sum in a second. Okay, we are going to see more variant of this question in further sums. Okay, now let's see this sum. This is of EC 2006. The input impedance and the output impedance ZO of the ideal transconductance voltage controlled current source amplifier. Another name of this transconductance amplifier R, and the option is ZI is 0, ZO is 0, Zi is 0, Zo is equals to infinity, Zi infinity, Zo 0, Zi infinity, Zo is also infinity. So if you see this question, this is also the same type that we have seen in the earlier sum. So the first thing what we do, we directly attack to the naming. Naming is transconductance amplifier, okay. So we have this transconductance amplifier, okay. Transconductance amplifier, it means at the output you will have a current and at the input you will have voltage, right? So if you write this transconductance amplifier into sampling and mixing format, what you can write this as, this will be at output and this will be at input, okay. So now you can write it as, at output we have a current, so we will write it as current sampling, and at the input we have voltage, so voltage basically series, right? So this is the format we are most aware of, okay. So now we can get our answer very easily. So you can see at output we have a current sampling. Current sampling, it means a series sampling. Series sampling, it means output resistance is going to, right, output resistance is going to increase, right? Series, it means increase. Now at input we have series mixing, it means input resistance is going to also increase. Now this is what we know, okay. But at the option you can see we have a 0 and infinity, okay. So what you have to do is, whenever you come across this option, you have to consider increase as infinity and decrease as 0. So you can see both are increasing, so both will be infinity. So you can see the correct option will be this D1. Okay, so you can see if you know this trick, you can solve this type of sum in a second. Now let's say this fourth sum, in a transconductance amplifier, it is desirable to have, this question was asked in EC07, EC14, EC17, just the wordings were different and the question was same. And the option here is a large input resistance, a large output resistance, large input resistance, small output resistance, small input resistance, large output resistance, small input resistance, small output resistance, okay. Same trick we are going to apply, we will attack on the name. The name here is transconductance amplifier. Transconductance amplifier, it means at the output we will have a current and at the input we will have a voltage, okay. At the output we have a current, so the naming will be current sampling, and the mixing we have a voltage sampling, basically series mixing, okay. So what we can see here is the output resistance is going to increase. Why? Because for current it will be series sampling and at input we have a series mixing itself, so input resistance is going to increase, okay. So both are going to increase. So from the option you can see this A option will be the correct, a large input resistance and a large output resistance, okay. Now let's see some another sum. This is a EC18 question, a good trans impedance amplifier has, and the options are same, okay. So for this also we are going to use the same trick. The trick says that you have to attack on the name. The name is trans impedance amplifier, okay. Trans impedance, it means that output we have VO and at input we have a current, okay, II, okay. So you can write it as voltage, at input we have a current mixing, it means a shunt mixing. I know you know this. If you don't know, please watch my previous video, you will understand everything, okay. Now we get the name, so we can get the effect on input resistance and output resistance very easily. For voltage sampling, it means a shunt connection, okay. So output resistance is going to decrease. At input we have a shunt connection, this means that input resistance is also going to decrease, okay. For shunt connection it will decrease, for series connection it will increase, okay. So the correct option will be a small input resistance and small output resistance, okay. So till now we have seen effect on input resistance and output resistance, but we didn't find the exact value of input resistance and output resistance. Now onwards we are going to get the exact value, okay. Now let's see this sum. This is of EC 1999. Yes, it is very old, but it is useful to show your mistakes. So the question says an amplifier has an open loop gain of 100, an input impedance of 1 kilo ohm, and output impedance of 100 ohm. A feedback network with a feedback factor of 0.99 is connected to the amplifier in a voltage series feedback mode, okay. The new input and output impedance respectively are, so basically we have to find out RIF and ROF, basically input resistance with feedback, output resistance with feedback, okay. Here also we are going to use the same trick, that is to attack on the name. The name here is voltage series feedback mode, okay. So voltage series we know, voltage series. From voltage you can say the type of sampling is voltage sampling, it means the output resistance is going to decrease, and at input we have series mixing, so we can say the input resistance is going to increase, right, because of this series mixing. But we want the exact value, okay. So to get the exact value, wherever you have increase, you will multiply input resistance with 1 plus A beta factor. This is basically a desensitivity factor. This is what I have told you in my first video of this feedback amplifier. For increase you are going to multiply 1 plus A beta, for decrease you are going to divide by 1 plus A beta, okay. So here you can see we have a open loop gain which is 100, we have Ri 1 kilo ohm. This is without feedback, okay? And RO we have 100 ohm. Beta also we have, beta is 0.99. Okay, and from this trick we get to know that output resistance is going to decrease and input resistance is going to increase. So for output resistance we will write as RO upon 1 plus A beta. So if you put the value, you will get 100 upon 1 plus A beta is basically 1 plus A is 100 into beta 0.99. Okay, basically 99 plus 100 itself. Okay, so 100 upon 100, 1 ohm. And for input resistance, we will write it as RIF. Since input resistance is going to increase, so we are going to multiply 1 plus A beta, RI 1 plus A beta. So it will be 1 kilo ohm multiply by 100, since this 1 plus A beta is equals to 99 plus 100. Okay, so it will be 100 kilo ohm. So from the option you can see the correct option will be this one. Input resistance is 100 kilo ohm and the output resistance is 1 ohm. Okay, so this is the way by which you can solve this type of question very easily. Now we are going to see the common mistakes we do in the next sum. Okay, now let's see this question. This is of EC 2003. Yes, new. An amplifier without feedback has a voltage gain of 50, input resistance 1 kilo ohm, output resistance 2.5 kilo ohm. The input resistance of the current shunt amplifier is given. Using the above amplifier with the feedback factor is 0.2. So basically you have to find this input resistance of this current shunt feedback amplifier. Okay, for this sum also we are going to use the same trick. The trick says you have to attack on the name. The name is current shunt. Okay, and we want input resistance. For input resistance we are going to see input side. At input side we have a shunt mixing. It means input resistance is going to decrease. Okay, so for same thing we are going to write it as RIF is equals to RI upon 1 plus A beta. This is what we have seen earlier, right? If there is a decrease you have to divide by 1 plus A beta, right? So you will write it as 1 kilo ohm upon 1 plus A is 50. So 1 plus 50 into beta is 0.2. So you will get 50 into 0.2, basically 10. So you will get 11 here. So the answer will be 1 by 11 kilo ohm, right? This is what you will say, but this is not the right answer. And I know you are going to tick this option and you will move ahead. But let me tell you, this is not the right answer. You have to be careful while solving this type of sum. You can see the question is of current shunt. Okay, and you must be careful that for current shunt we want a current gain. Okay, but here we have a voltage gain. Now you may be thinking why we want this current gain. So for you I'm going to derive why we want AI. So you know, for current shunt, it means at output we have a current sampling and at input we have a current mixing. Okay, so at both the end we have a current. Okay, so the gain will be here output by input, basically IO by II. So you can see it will be the current gain here. Okay, but in the question we have a voltage gain. Okay, so the first step you have to get the current gain. Okay, so to find out the current gain you must know this relation. AV is equals to AIRL by RI. RL is basically a output resistance, RI is basically input resistance, AI is current gain, AV is voltage gain. Okay, so from this formula you can write it as AI is equals to AVRI upon RO. Since we want AI, so I have shifted RI and RL there. Okay, so I got this equation. AI is equals to AVRI upon RO. So we will get AI as AV is 50 multiplied by RI. RI is 1 kilo ohm and RO is 2.5 kilo ohm. Okay, so this KK got cancelled. 50 upon 2.5, basically 5 by 2. So you can write it as 100 by 5, basically 20. So we get our current gain. Now we can use this formula. So we will get RIF is equals to RI1 plus A beta is equals to 1 kilo ohm upon 1 plus, now A we have this current gain. This is what 20 multiplied by beta is 0.2. So if you multiply it, you will get 1 kilo ohm upon 20 multiplied by 0.2, basically 4, right? So 4 plus 1 will be 5. So 1 by 5 kilo ohm. So you can see from option this B will be the correct option, not A. Okay, so be careful while solving this type of sum or else you are going to lose marks. Okay, so that's it for today. Thank you guys.